Who doesn't love? Yes, so we will be talking about the topic of dark energy tonight. Hi, Delaware. Hi, Megan. We're going to be talking about the topic of dark energy from physics, specifically from cosmology, astrophysics, astronomy. That's my field, and we're going to be talking about that tonight here on the live. So please join in. Just scroll by what's going on here. Who doesn't love Neil? Hi, Megan. Hi, Delaware. Hi, Megan again. Hi, Make It Zero. Hi, Experiment. One of these is a college textbook. Yes, one of them is. One of the books I tagged, which I also use a lot for the channel, is actually a college textbook for majors in astronomy. You must be looking at this one. See, this one right here. It's a very good book and a college textbook. Yes. Some people actually want to know what these books are that I use on the channel. So therefore, it is tagged. But also, we're going to use just this book tonight. Well, we can use other books. It really depends on how the live goes. But this one is going to be the Neil deGrasse Tyson book, Astrophysics for People in a Hurry, which is a really, much more light read for the topic of dark energy, okay? And we're on the dark energy chapter, and we have already covered the first part and talked about it and things like that last night. So this channel, we talk about physics, astronomy, astrophysics, cosmology. We also show kitty cats, we show my face, we talk about physics and my background, and well, utilizing my background, we go over these very interesting topics that, I enjoy and a lot of people on the channel enjoy. Tonight, we're going to continue with our dark energy discussion that we started last night. And yeah, that's really what's crack-a-lacking here. That's what's going down, okay? Hello, Running Man. Hello, Altriano. I love smart girls. Oh, thank you. Hello, Jaden Smith. What's good? Hello, Make It Zero. Energy is just light, sound, and vibration. Hi, Make It Zero. Hi, Jaden again. Much love and thank you. Hello, Prod by Hit Baby. Okay. Some of you have very interesting usernames. I am trying to give everybody a shout out, and sometimes sometimes I have to be careful because it's not really something I can say out loud. But I eat crayons. Green is the best. Hello, Boot Beltran. Sleek Hobbies. Hello. Go to Spotify. Books are full of. Okay. Hello, everybody. With the business, you're beautiful. Thank you. Ali Khan, any books besides astrophysics, anything regarding linguistics or philosophy? Those are not really my expertise, so I'm mainly just sharing from my field, which is physics. I love Neil deGrasse. How many cats do you have? I'm not going to tell you because you're going to have to find out by coming to my lives. So I wanted to say that I have very many lives that are posted already on the channel under the live tab of my channel. So this has been going on for over a year now, almost 2 years. And we have many, many episodes. So if you enjoy these types of topics, then I would go and check out more of these under videos as well as under the live tab where all the live episodes get posted. And you might find many things that you would enjoy, and leave your comments for us and things like that. Give your input. That would be much appreciated. And also, some people actually find this to be a physics ASMR channel where they play the videos and sleep to it. So it's also called soothing physics. Okay. Once you have subscribed to this channel, your life is changed forever for the better. I do hope anyways. Thank you so much for being here. One time, a Chinese man asked me for directions, and I sent him walking extra 5 kilometers. Hello, Patiently Happy. Hello, Ali Khan. Excuse me. Hello, Miguel. Hello, Sleek Hobbies. Hope your day is best. Thank you. Subscribe and... Ben, why are you sending them to Spotify? Unless Spotify is advertising and sponsoring us, we don't want to send them to Spotify, okay? Altriano is saying, make it 0. I concur. I love you. Hello, Kevin. I never put my phone on silent mode when in theaters. Oh my goodness. They really do go. Okay, hello, Tony. I'm in Boston, Massachusetts. Patient based. Can you drive a stick shift car? I could a long time ago where I got my license for the first time, but now probably not. Sometimes I use the Bible as okay. Hello, patiently. Hello, Mahadevan. Hello, Execute. Hello, Eddie Long. Hello, Dylan. Awkward. Hello. Hello, Tony. Hello, Jefe del Gato. What was just rude? I know a deep threat. Hello, Alex. IDKE Hawaii. Hawaii. HY. Uh, okay. Hello, IDK. Outside 365, hello, you look like a Pixar animated character. Hello, Hefe. Hello, Dylan. Hello, Fatuma. Hello, Ben. Hello, Religion. Hello, Meow. L. Zoro. Okay, everybody, thank you so much for being here. You should get your hair dyed. Okay. I casually like to drop banana peel. You guys are funny, but go ahead and dominate the chat. This sounds like a usual night for us, so we are not easily phased. If you're trying to get a reaction, by the way, just remember I've been doing this for almost 2 years, so it's not very easy to get a reaction unless I really want to give one for for added drama here. So we will now get started. I will share the live from my other phone, and then actually I need some water in my water bottle, and I'll be right back. And we will get it going. I have been busy with taxes, so I've had to do shorter live stream episodes lately. And by short, I mean it's still over an hour long, okay? Because we have had live streams that were more like 6-7 hours long, talking about physics and everything else. So settle in, grab a snack, grab a drink. I will be right back. Thank you, Ben, once again for being here and modding, by the way. Really helps me out. If you do, help me with my super chat goal, that also really helps me out. And so on and so forth. Let me share the live. Okay, we're live. Where is Reese? Are you here? My mod in Britain. I miss him because he has interesting additions to the chat sometimes. I haven't seen him in a couple of days here. Okay, this is going to be a dark energy study with me. We are live. I'm telling my channel. Hi, Wild and Fresh. How are you doing? Oh my goodness. I see more of you here. Hi, Sriram. Okay, in a moment, we will do the top fans and hopefully many more of you get shout outs there, okay? Can you teach me some math? Hello, Nature Maid. Oh. Perfect time to class. Yes! Hello, Bliss Gang. Hello, Happa Nappa. I like Napa. So Happa is fine too, I suppose. Okay. Let me get my water. Whew. I had a Gatorade at the gym, got one. I don't like that I got it at the gym, but I kind of needed one. Because, you know, the vending machine costs more than just buying a pack of Gatorade. But now I have this bottle. Now I will be using it. Filled it up with water, and I will not be throwing it out immediately. Yeah, because at the gym, the Gatorade costs $3. And I don't like to overpay for things at all. But I did feel like a Gatorade was much needed tonight, so I got one, this orange flavor one. Anyways, so I wanted to do a little bit of a recap, but not without, you know, too much repetitiveness, because I did give you a long spiel last night when I talked about dark energy. So the people who were here already, or if you're kind of listening to this in an order, as a, you know, sort of the playlist and kind of going down the list of these episodes, because I know some people do listen to the live upload later on and whatnot and leave their comments, which I very much appreciate. So if you're seeing this as a video upload, you know, later on and did not catch this as a live, then worry not. Please do leave your comment and your thoughts in the comments section, because that also really helps me, and you can leave me your thoughts there. Now, of course, if you're here live, then that's the best part. You can put your chat messages live here in the chat, and I will see them, and you can also discuss with each other. Ben here has been providing some really nice, useful information in the chat to kind of go with the with this audio portion. Okay, so audio video portion. So there's that as well. So hopefully you get a lot of value out of this experience. And generally, when people spend some time on these lives, they usually come back, and you know, they hopefully you subscribe and keep coming back to listen to these topics more and more. And we try to cover many such topics. So this is not going to be the one and only or anything like that. But without being too repetitive, I wanted to remind you that this is a cosmology topic. So physics has many subfields, and cosmology is the study of the universe. So the total universe and topics related to that, such as the beginning of the universe, the origin of the universe. Sometimes we call that the Big Bang, because it is the, you know, popular slash kind of winning theory for the origin of this universe. The evolution of the universe, how it has expanded, how you know, there are galaxies now, but there weren't galaxies a long time ago. So of course the universe has gone through stages of evolution, and really it has these different eras. It used to be what we could call radiation dominated universe in the more towards the beginning. Then it, you know, later on became more of a matter dominated universe, and currently a very important slash the most sort of important game in town for a cosmic ingredient in this universe that we are a part of is dark energy, which is a thing we are researching, so we don't really fully understand it, and we don't really quite get what exactly the physical meaning of or nature of this thing is. But we consider this important, of course, because it is leading to an accelerated expansion of the universe. And you know, there's after doing observations and math and looking at the energy density, it turns out that it's actually contributing a large portion, the majority of the energy density of the current universe. So dark energy is important. Now, why it's called dark energy is because it is somewhat of a mystery. So dark energy, kind of like dark magic, like some people say sometimes here, you know, a little bit of it is like that, because, you know, dark magic is what? Is something we don't understand, a mystery, something that is confusing, something that is not fully understood. And basically dark energy is kind of like that, okay? So partly the naming is because it is still a mystery, and it is, you know, kind of this unknown, but it's also driving an important, you know, thing in this universe, a very important, you know, maybe the most important thing after gravitation, and it's actually being gravitation. So gravitation pulls things close, makes matter clump, but this thing, dark energy, is making the universe expand And that too, more and more like the farther away you go. So like the most distant galaxies from us are receding faster and faster the farther away that they are. So that phenomenon of the universe's expansion is called is you know, we say dark energy is responsible for that. Okay. Partly because we don't know, partly because, you know, we want to call it some kind of energy because, you know, some people say it's a negative energy or a negative pressure of the vacuum and whatnot. Well, you know, whatever it is, it's not fully understood, and so we research it, of course, as a current topic. But energy, I guess, is sort of part of the name because of that, and the dark part is sort of because we don't fully really get it. Okay. So that's the topic for today. As you of course can imagine, this falls under the cosmology subfield because definitely, unlike other topics that we have also discussed here, this really affects our universe as a whole. And because, you know, those distant galaxies that are receding from us even faster than one would expect, that has to do with expansion of this universe. That is not a local effect. Okay, so cosmology is the science of the cosmos, science of this universe, what's happening in this universe. Local would be something like our solar system, our galaxy, or even our neighboring galaxies, like the local cluster, right? So the local cluster has some localness to it because everything is relative anyways, but you know, Milky Way is part of a group of galaxies. It's called a local cluster. We have, you know, other galaxies nearby, sort of nearby, not really that nearby, depending on what you consider nearby. But, you know, compared to the farthest away distant galaxies, of course, Andromeda and our neighbors are nearby. Okay. So in this type of scales, it's not felt. This phenomena is not really felt. It's really about those distant galaxies and how they're moving farther and farther away at an accelerated speed and at more acceleration than we would have expected for the expansion to happen. And we saw the evidence of this in 1998 from the you know, the multi-group or multi-team effort that we also mentioned about last night. We saw that a number of groups, all competing groups, so they're not the same people, you know, so they didn't have to agree and come to the same conclusion because these are different groups working on this. They got they got these supernovas data set. They used the supernovas as what they consider in astronomy standard candles, and you know, they're expected to give you basically the same luminosity, peak luminosity, if not for the distance away that they are from us. And those standard candles were good standard candles and whatnot. And basically the discrepancy they found was due to this expansion, and it became this strong evidence for this, oh my gosh, something out there is doing this expansion, and what is it? So then this phenomenon was solidified as this dark energy thing, and we started to call it dark energy. We could have called it other things in the past. We mentioned how in Einstein's equations, the way when he first introduced it, which is really the historical mathematical first introduction that I know of anyways of dark energy, is, you know, we called it cosmological constant at that time. He called it cosmological constant. So sometimes you might hear that too. Cosmological constant. Cosmological constant, and the basis of that was that it would be this term that balances out gravitation, because Einstein worked on gravitation, gave us general theory of relativity. He wanted something to basically keep the universe static against gravitation and not have it collapse. But turns out that the universe was actually expanding. He was, you know, kind of embarrassed that he didn't, you know, predict that, but that's okay. We forgive him. You know, Hubble gave us that, and we, you know, Einstein gave us many things, and the cosmological constant as a construct and something that we can kind of fall back on when we come across this type of behavior of this universe is credited to Einstein. So dark energy, cosmological constant, these things are pretty much the same, if not, pretty much related, if not the same. At this point, there would be probably more, sort of more, more diversity or more variety in the models that take into account or that try to treat dark energy than just the cosmological constant. But those are details that we don't have to get into right now. So pretty much when you hear cosmological constant, this is what it is that we now call dark energy. Okay, so this is the cosmology topic that we have been covering yesterday and today. If you saw my video yesterday, you would have gotten more information. We covered quite a bit from this book. This book by Neil deGrasse is the one we're using at the moment. We've used and pretty much consulted from lots of other books as well on this channel, and for the exact purposes of this topic too, we've actually covered from multiple books. So I wanted to mention that because this book is kind of nice because it covers it at sort of this high level, but we have covered it in a bit more detail from other sources. So one such other book is, of course, this one, Modern Cosmology, by Scott Dodelson. This is kind of a dense book. It's sort of a reference book. Lots of, it's not exactly, the story is not exactly told in a very, people-friendly kind of way. But, if you went to grad school or something for physics, you'd probably have one of these if you're pursuing cosmology, okay? The shoutouts are great, but it's this all. Why are you saying my name? Okay, so I'm looking at some of your comments, but I am going to keep on going with the topic and then come back to your chat messages, okay? Okay, I will keep coming back to your messages. If I see a question, I'll try to address it as best as I can, but if not, then oh, somebody asked about string theory. Okay. So by the way, we have a bunch of episodes on string theory. We will not be covering string theory tonight, but we have actually gone over it quite a bit in the past. So hopefully, if there is a topic that you are looking for tonight, hopefully you find that under the live tab of my channel there, or come back another time, and we'll probably get there again. Sometimes we repeat the topics, but every time we generally present it kind of slightly differently or with some more insights. So it is useful to come to the lives, over and over. And also it's all recorded and posted on the channel. If you go down the list of lives, you'll find string theory, but I'm not sure that we will cover it tonight. Maybe. Hi, Randy. Thank you, Altriana. Okay, so we will get started once I sip some water, okay? Did I share the live? I think I did. And can we get 50 likes, please? I hope that people are ready. So let's continue from where we left off last night, okay? All right. The shape of our four-dimensional universe comes from the relationship between the amount of matter and energy that lives in the cosmos and the rate at which the cosmos is expanding. So keep in mind, we're going to be talking about the energy density of this universe, okay? So we're not talking about this galaxy or this solar system, but about this universe. And we mentioned what the 5 cosmic ingredients of the universe was yesterday. So that is going to be one of the quiz questions. Ben, you can say one of them. So once again, shape of our four-dimensional universe comes from the relationship between the amount of matter and energy that lives in the cosmos and the rate at which the cosmos is expanding. Because as you can imagine, if the cosmos expand, then that also affects the energy density of the cosmos. A convenient mathematical measure of this is omega. So in cosmology, when we say omega, we mean the big omega. So sometimes it's called big omega, but the big omega symbol is different than little omega. Big omega is like this. Little omega looks like a W. So hopefully you caught that. Let me, can somebody put big omega in the chat, please, as a symbol? Maybe Ben can do it or somebody else, but hopefully we can, but hopefully we can see that in the chat, okay? Hi, Wild and Fresh. Maybe I'll have to do it because you guys are looking a bit distracted. Let me put big omega in the chat. Unless Ben beats me to it. Okay. I really want to put this in. Sorry. You guys are not the most yay, big omega symbol. Did you do it? Love this girl too much. Thank you, Wild and Fresh. That is nice. So can we get 50 likes, by the way? That wasn't a very, let me do another one. I'm copying and pasting a big omega symbol, and it's not showing up quite the way I would want. That box is not a box, it's a part of a cat tree. See, there's more. Wall cat tree. Climbing tree. Okay, there is omega. Big omega. Okay, so I put big omega in the chat so you know which symbol we're talking about. And this big omega is that's the one we're talking about right now, okay? A convenient mathematical measure of this is big omega, yet another capital Greek letter with a firm grip on the cosmos. excuse me, if you take the matter energy density of the universe and divide it by the matter energy density required to just barely halt the expansion known as the critical density, you get omega. So this big omega is pretty much the matter energy density of the universe, and divide that by the matter energy density required to just barely halt the expansion of the universe, then you get the critical density. Now we will see how it's used, okay? We're doing just a tiny bit of cosmology math, okay? Since both mass and energy cause space-time to warp or curve, omega tells us the shape of the cosmos, okay? So this big omega is going to be important in various different cosmological models, depending on, you know, the value of omega or what you allow omega to be in your numbers or range of things that you're considering. You're going to get a different shape of this universe, okay? So if omega is less than 1, the actual mass energy falls below the critical value, and the universe expands forever in every direction for all of time, taking on the shape of a saddle, in which initially parallel lines diverge, okay? If omega, so this was when omega is less than 1, okay? So once again, let's define what omega is. Once again, if you take the matter energy density of the universe and divide it by the matter energy density required to just barely halt the expansion, which is known as the critical density, you get omega, which is that big omega that we put in the chat, because that's the symbol that is commonly used for this, okay? Now, both mass and energy will end up causing space-time to warp. We know that, for example, gravitation, the way it's described in general relativity, of course, is a dimple in space-time caused by a massive object in its locality, right? So space-time curves, space-time is curved by mass and energy, because mass and energy, by the way, in relativity are equivalent. So if mass is gonna bend space-time, so can energy, in a sense, okay? So once again, remember general relativity takeaway from last night and other nights. General relativity says that gravitation, or basically a massive object, is gonna curve space-time or put dimples in space-time, where space-time is this fabric, if you will, four-dimensional space-time is the fabric that's getting curved by something like a massive object in the locality of that massive object. It's basically putting a dimple in space-time and making things go on these geodesics. Like, for example, the Earth going around the sun is the geodesic, or the straight line in that curved space-time that Earth is made to follow because of the sun's gravitation. Okay, so the sun's gravitation is putting the dimple in the four space-time that makes the Earth orbit the way it does. So even though the Earth may look like it's following a curved path, actually in four space-time, it is following a geodesic, or the straight line version of four space-time, okay? Because four space-time geometry is different than Euclidean geometry, which is the one we're more familiar with. So general relativity just has this other type of geometry, and in that geometry, gravitation actually makes things follow the straight lines of that geometry. So, and we also know from relativity, so see, a lot of this stuff just falls right out of relativity, okay? It's not that foreign to talk about the universe, because relativity gives us the tools, right? So the other thing we know from relativity is about mass energy equivalence. You guys know about it too. E equals mc squared is basically this mass energy equivalence, right? The sort of fallout from that. So by the way, it's E equals plus or minus mc squared, but that also comes from that, right? So if mass is bending space-time, so can energy. Both mass and energy will bend space-time. So it doesn't, at some point, whether it's a mass and energy, whatever it is, and whatever is kind of contributing to the energy density in this universe, we know that it's gonna change the shape of the universe, right? That much is done. So pretty much now we are considering what kind of universe do we live in, right? We won't know everything about the universe, but we can certainly try to understand it better given what we do know. So this omega thing is very important because it lets people kind of imagine different models of the universe. And of course, the one that matches with observation is going to be the one that wins at the end of the day. And we'll be like, oh, okay, I guess that's the universe we live in. But remember that in the mathematics, in the modeling, in cosmology, you can dream up different types of universes. You can have a universe of a certain shape, another one, and another one. Okay, like there's no limit to your imagination, really, in the sense of the math and what you're doing in the modeling of cosmology. But of course, at some point you should anchor your model in the observation and make sure that it's anchored in the current reality, because of course, again, the universe is changing. The current reality is simply the current reality. But basically this is the math of that energy density business, because we want to understand, for example, which type of universe we live in, what shape, right? So that's what's going on here. And for that, just keep in mind, this omega thing is very important. People deal with this a lot. Okay. Thank you, Brawler. So big G, so I just want to caution that the 9.8 meters per second squared is the acceleration due to gravitation here on Earth, and that is usually denoted by small g. Big G is the gravitational constant, and that is a different value, okay? Yes, please subscribe. So we don't want to call 9.8 meters per second squared, which is simply the acceleration due to gravity here on Earth. It's not going to be the, obviously it's not the same other places around other massive objects. That is simply the gravitational acceleration here on Earth. So in Earth's gravitational field, that's what we're all feeling, right? But that is denoted by small g. I just wanted to note this because it's rather important. When I mention about big G, that is the universal gravitational constant, and it is an important constant even in general relativity. Okay, so please do keep that in mind. And yeah, small g is of course 9.8 meters per second squared. Of course, light gets bent. So somebody asked, wonder if light gets bent. Does that slow down time? Yes, of course, light gets bent. Light is the bending of light is one of the predictions and results of general relativity. General relativity predicted the bending of light, and that was confirmed. So yes, light of course bends, and that's the same reason why light cannot escape a black hole. Light is bent by the gravitational field of a black hole, lots and lots, so much so that it cannot leave, okay? So of course light can bend. Hi Acacia, ¿cómo estás? How are you doing? Hi Hafiz. Tanning remedy, please, your skin shines. Light takes time to reach us. A finite time to reach us, because the speed of light in vacuum is a constant. And it's a finite constant. So it takes time. But as far as the bending and whether, like, how much it bent and all that stuff, you can see and measure. And it won't take the same time always, because Just quickly looking at all the comments. Thank you once again, Brawler. But okay, I wanted to really quickly say that small g is not the same as big G. Keep in mind there are two G's in gravitation and in general relativity. Big G is the gravitational constant. Small g is just to do with our Earth. Okay? I guess so. Somebody asked, can a nuclear blast warp the space-time fabric? I would tend to say yes. Okay, perfect. I think I kind of see your comments and I can get back to them once I see if there's a question, okay? Okay, we'll keep going. So, since both mass and energy cause space-time to warp or curve, omega tells us the shape of the cosmos, okay? So depending on what omega we end up getting, because we can think up various omegas, but the one that we get is going to tell us the shape of this universe. So if omega is less than 1, which means that that ratio that we just talked about is going to be less than 1, right? Then the actual mass energy falls below the critical value, and the universe expands forever in every direction for all of time. Because remember, in that ratio, the denominator of that ratio has the matter energy density required to just barely halt the expansion. So if you're less than 1, if the ratio is less than 1, that means that the matter energy density required to just barely halt the expansion, that's going to be more, right? So basically what that means is that the universe is going to just forever expand in every direction for all of time, taking on the shape of a saddle, okay? In which initially parallel lines will diverge. So yeah, that's going to be the meaning of omega less than 1. Because we're basically defining a ratio and then we're considering what values mean, right? So if that ratio is less than 1, it means the universe is expanding forever in every direction and parallel lines will diverge. If omega equals 1, then the universe expands forever, but only barely so, because that ratio of those two things equals to 1 means that barely expanding universe is basically the truth, okay? So in that case, the shape is flat. So this is what we call the flat universe. Not flat Earth, but flat universe, okay? Thank you for liking the live, by the way. Appreciate it. If you can help me with the super chat goal, that would be appreciated as well. Or just comment, chat messages, things like that, okay? So if omega, which is this important thing in cosmology that we mentioned, that we're defining, if that thing is 1, then that means that that barely expanding scenario is the one, okay? So that's the reality. So if omega equals 1, the universe expands forever, but only barely so. So not bad, right? Not bad. In that case, the shape is flat, preserving all the geometric rules we learned in high school about parallel lines. So in a flat universe, two parallel lines will never meet. But in a saddle universe, two parallel lines will start to diverge. Like they'll go like this in a universe that's expanding forever and ever in every direction without check. Okay, so it's going to look going like this. But in a flat universe, what we call a flat universe is this case, okay? Two parallel lines never meet. Now, if omega exceeds 1, then the parallel lines will converge and the universe curves back on itself. ultimately recollapsing into the fireball whence it came. So we don't really, I don't know that we would want this one where omega exceeds 1, which means, because again, remember the denominator had the barely expansion case, right? Energy density needed for barely expanding. So if omega equals to more than 1, then that means that the expansion is not enough, okay? What happens if the expansion is not enough and that numerator is more, right? So in that case, what would happen is that the universe would start to contract and collapse on itself, ultimately recollapsing into the fireball whence it came. So there we have it. Okay. So yeah, this, all this can be obtained from general relativity. General relativity gives us a way to treat space-time, mass, energy, all this stuff. So pretty much depending on sort of your energy density, mass energy density, all this stuff, you get the shape of the universe and you get sort of the fate of the universe. Expand where? Expand everywhere. We are in the universe, so it's not like it would, it's not like I'm in Boston and the universe is going to expand in, Baltimore. We're all in it, so we're all gonna expand. Oh my God. If it's more than 1, if omega is more than 1, then the universe contracts. Hi, Matt. You're not too old. Keep on listening and keep coming back to the lives. You're gonna do wonderfully. You guys are funny. Expand where? Oh my God. Cosmology. As I teach cosmology, people ask me about cosmetology, which is the study of makeup. And someone was asking about my tan. Dude, this is just my skin color. Thanks to God. Thank you to the universe. Oh my God. I couldn't keep it together. Now I'm choking. Shouldn't have laughed. Hi, something more. I know I'm talking too much. So you won't get mad. Mad about what? Have you ever heard of gravitational? Hi, Bryce. Hi, Ali Khan. What is the sine rule of omega? Sine rule. What do you mean? We're considering omega being more than 1, less than 1, and 1. Because omega is a ratio. Hi, Marcus. Please explain to me why my work doesn't have a matching 401k. Oh no. That's not good at all. Do I think there are different rules of physics in a vacuum? No. I don't think that. Is gravity a push or pull? Gravity is what curves space-time. Puts dimples in space-time, in the fabric of space-time. Okay. I can't look at the chat because it's making me laugh too much. Can we get 100 likes? You guys, this is a serious topic. Don't be like that. All right. We're going to keep going. At no time since Hubble discovered the expanding universe, because that's what Hubble did, remember, after the theory of general relativity came out, where Einstein had given us the cosmological constant and basically attempted to have a static universe by, basically the cosmological constant was such that it would be an anti-gravity term, kind of balancing out gravity and not letting the universe collapse. But then Hubble goes and shows observationally that the universe is actually expanding. So that was a big moment for us in cosmology, astronomy, and also a big moment for Einstein, who thought that he had really messed up. Okay? So we talked about this last night as well. So at no time since Hubble discovered the expanding universe has any team of observers ever reliably measured omega to be anywhere close to 1. So pretty much we've been making the observations and we don't really see omega to be close to 1. Adding up all the mass and energy their telescopes could see, and even extrapolating beyond these limits, dark matter included. So dark matter is the other important cosmic ingredient we've mentioned, separate from dark energy, not the same as dark energy. So dark matter included the biggest values from the best observations topped out at about omega equal to 0.3. So pretty much ever since we have known about the expansion of the universe, whenever we measure omega, we find something like 0.3 as the max value. We don't really see it get close to 1, okay? As far as observers were concerned, the universe was open. for business, riding a one-way saddle into the future. Meanwhile, beginning in 1979, the American physicist Alan Guth of the Massachusetts Institute of Technology and others advanced an adjustment to the Big Bang theory that cleared up some nagging problems with getting a universe to be as smoothly filled with matter and energy as ours is known to be. So let's see about that. A fundamental byproduct. So this whole smoothness of the universe is also something we've talked about in cosmology in the past. You should look at my cosmic microwave background episodes and whatnot. A fundamental byproduct of this update to the Big Bang was that it drives omega toward 1. So for the longest time, we found omega was just about 0.3 was the max. But then there was an adjustment to the Big Bang theory that cleared up some nagging problems with getting a universe to be as smoothly filled with matter and energy as ours is known to be. This update happened in 1979, and a fundamental byproduct of this update to the Big Bang was that it drives omega toward 1. So not toward a half, not toward a 2, not toward a million, but toward 1. Now, do you remember what 1 means for omega? It's not bad. If omega equals 1, the universe expands forever, but only barely so. Not bad. Hardly a theorist in the world had a problem with that requirement because it helped get the Big Bang to account for the global properties of the known universe. There was, however, another little problem. The update predicted 3 times as much mass energy as observers could find. So this update to the Big Bang theory helped with other things. It helped with other consistencies from that Big Bang theory and its predictions. But there was this other problem where it did also mess up sort of this prediction for the mass energy in the universe. It predicted more. Undeterred, the theorists said that the observers just weren't looking hard enough. So, you know, you can always say that there is mass energy in the universe that we just don't know about yet. And that's pretty much what they were saying. So at the end of the tallies, visible matter alone could account for no more than 5% of the critical density. So now we're coming up with those tallies we mentioned last night, the cosmic ingredients. Who is contributing what to the energy density of the universe? And it turns out that the ordinary matter, everything that you and I are made of and whatnot, all the stars, all the galaxies, this only accounts for 5% of that critical density. And because now we're at the critical density, as in the density that would lead to that omega just about equal to 1 scenario, remember. So if the energy density, the mass energy density, if it's not, pretty much, if it's not at that critical density, because remember what the definition of omega was? If you take the matter energy density of the universe and divide it by the matter energy density required to just barely halt the expansion, that's omega. So that scenario of barely halting the expansion, that is called the critical density. So if you're saying that omega is basically equal to 1, just about equal to 1, meaning that you are just about at that critical density, then it also turns out that the critical density is contributed to only 5% of that comes from ordinary matter. Okay? So they added that too. Nobody knew what it was, and we still don't know what it is, but surely it contributed to the totals. From there, we get 5 or 6 times as much dark matter as visible matter, but that's still way too little. So they also found that there was this thing called dark matter, which is also under, investigation exactly what it is. But basically, dark matter was present as well, and it was way more than ordinary matter. Um, but that still did not account for all of the mass energy. So observers were at a loss, and the theorists answered, keep looking. Both camps were sure that the other was wrong until the discovery of dark energy. So pretty much when dark energy was discovered with the 1998 observation and that all that stuff we talked about with the supernovas data set, it wasn't like, sure, it was kind of a big deal, but also it was the answer to this question, which is about the missing mass energy and the missing contribution to the energy density, which would explain our current geometry of the universe and the shape of the universe, and the fact that that the energy density is equal to the critical density, pretty much. So that single component, when added to the ordinary matter and the ordinary energy and dark matter, so when you add in the component of dark energy to ordinary matter, ordinary energy, and dark matter, then you get the mass energy density levels to where we would need them to be, which is the critical level. And what is the critical level? The critical level is the level at which you get that barely, you basically get expansion forever. You would pretty much not ever collapse or contract. The universe would not really collapse or contract, okay? So in that sense, it's good. In that sense, it's good, right? Like we wouldn't really, I don't think we would want a contracting universe. It's just, we don't exactly know what dark energy is, but it seems like there is this thing, a lot of this thing, which makes the universe energy density be close to the critical density, which would be the barely expanding case, which would make us expand forever. Okay? So just keep in mind that these things are coming, there's a lot of different pieces to the puzzle here, and you're getting the different pieces from different parts and different types of work. And only the right piece will fit in properly, okay? The wrong piece will not fit, just like in a puzzle. So it's not the case that you just kind of, put everything together that you know. It's also the slowly developing story, and then you get one piece from here, one piece from there, and you're putting it all together, okay? So for the first time, the theorists and observers were agreeing. Both in their own way were correct. Omega does equal 1, just as the theorists demanded of the universe, even though you can't get there by adding up all the matter, dark or otherwise, as they had naively presumed. There's no more matter running around the cosmos today than had ever been estimated by the observers. So the observers had seen what matter they're dealing with. There's the ordinary matter, and then there's also dark matter that they had found. Dark matter, exactly what it is, we don't know, but they did find it. They saw the gravitational effects of it. So they're considering even that. So now what is left, right? They don't know if it's going to be some kind of matter that they have to find still. And turns out that they didn't. This is about dark energy, okay? So this is why they call dark energy, because even though we've talked about mass energy equivalence, but basically this is more of an energy energy thing that's going on, which is a mystery. But it's not like we had to find some kind of like extra galaxies out there or something dark or otherwise, okay? Nobody had foreseen the dominating presence of cosmic dark energy, nor had anybody imagined it as the great reconciler of differences. So they didn't really, so this came as a shock, especially when you put all of this math together and realize that dark energy contributes to 68% of the energy density. Dark matter contributes 27%. and then ordinary matter contributes only 5%, that does, even though it makes all those other things line up nicely, it gives you the critical density, it gives you a way to be consistent with the Big Bang, it it makes the universe a nice shape, it gives us forever expansion without being too crazy. But at the same time, it begs the question also, what in the heck is this dark energy? Because it's such an important contributor to the energy density, but it is not, what do you call? It's not really something we totally understand. Like, what is it? Okay. And the same kind of goes for dark matter, honestly. We don't really understand what dark matter is either, but we see without fail its gravitational effects. Okay. So, so because dark matter has gravitational effects, we call it, we would call it more of a mass thing, something with mass, something that interacts gravitationally. Why? It could be some kind of weird thing that does not, clearly does not interact with light, does not do nuclear fusion, only, we only know its presence through gravitation. But it behaves like more of a matter. But this dark energy thing that is responsible for the expansion, acceleration, that that is some energy, some kind of something that's in there, that's out there, out there, whatever, part of this universe. And we don't exactly understand what the something is. We may call it certain things like negative pressure of the vacuum and this and that, but we don't fully get it. Okay. And this is why we are researching it, right? So oh my goodness. Oh, thank you, Gary. Gary has done a super chat. Thank you so much. Hi, Jared. Hi, Oscar. How are you doing? Okay, perfect. So, thank you so much for the help here, for the super chat. Thank you so much. Let me change my goal. Make it a little easier for you guys. Wait. I'm glad to be here with you, dear love. Oh, hello. How are you doing? Hi, Jim. Today it's timeout day. It's actually not letting me. Oh, there it is. I don't know. It's not easily letting me change my goal. No, 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 Hi, Wild and Fresh. You want a timeout? That's interesting. Okay. While do you like timeout? Hi Shakuni, how are you doing? Hi Zain. Yeah. You haven't been here in so long, Shakuni. Okay, for whatever reason, it's not. It's not letting me do a goal. Let me try with my other phone. Did you guys subscribe? Did you guys subscribe? Did you? Did you? Did you? Did you? Thank you, Wild and Fresh. Hi, Proud Indian. Hi, Zain. This is the first time I've seen a person like you. Hello, Shakuni. Hi, Tony. Very weird, some of these comments, but it's okay. Ben, can you take care of this Jared guy? Okay. That's me. Petrol. Oh, let me do the top fans really quickly. I didn't look at my top fans today. Number 1 top fan of today is Tony. Hello, Tony. Thank you so much. I hope you subscribed. Number 2 is Ben. Ben, of course. Thank you. Number 3 is Wild and Fresh. Number 4 is Megan Collins. Hello, Megan. Number 5 is Spartacus. Number 6 is Meow. El Goded. Number 7 is Tapes or CDs. I suppose maybe Tapes. Number 8 is Jaden Smith. Hi. Number 9 is Confused Biscuits. Number 10 is Adrian. Number 11 is Ali Khan. Hello. Please do subscribe. Number 12 is Happa Nappa. Number 13 is Delaware. Number 14 is Blood Sealed. And number 15 is Bryce. Thank you so much, guys. Okay, we will keep going and hopefully that will clear up some of these things as well. So, the shape of the universe, as somebody pointed out here, is determined by the mass energy density. We talked about this omega business, which is basically a ratio. And depending on the value of it, whether that's greater than 1, less than 1, or 1, you would have a different geometry of this universe. Currently, it looks like we have a flat universe, and it did require a bit more mass energy density than we were observing, but then we got this accelerated expansion of this distant galaxies and whatnot, and we had to kind of revive the original cosmological constant from GR and pretty much accept that there might be this extra mysterious thing causing the expansion of the universe, which is called dark energy. And dark energy has a dominating presence, it looks like, and contributes in a dominant way to the energy density, especially for it to be equal to the critical density of this universe. Hi, Tune. Leaving this on in the background for ASMR. Yes, please do. Leave this on in the background for ASMR. It is kind of like an ASMR. Can we get 100 likes? Dark energy has the opposite effect of gravity, but exactly what it is we're unsure. So we would like to understand it better. We would like to understand what is the physical, nature of dark energy. What exactly is it? But it does have the opposite effect of gravity, as in it makes the universe expand at an accelerated pace, farther and farther away from us. And it does act as an anti-gravity term in our equations for the universe in general relativity, for example. But exactly what it is, what this physical quantity or whatever it is, can be, it is sort of an unknown to us. So that's why we have to keep on researching it, okay? Okay, so what is this stuff from the book, okay? Nobody knows. The closest anybody has come is to presume dark energy is a quantum effect. So that's what I'm saying too, is that nobody really knows, right? Nobody really knows. The closest anybody has come is to presume dark energy is a quantum effect, where the vacuum of space, instead of being empty, because it's conceivable that we call dark energy basically this negative pressure of the vacuum, right? Something that is making our universe expand, especially more and more expansion as you go farther out. So it is conceivable that there is something going on in the vacuum that's kind of doing that. And I'm calling it something because I don't know what it is. We don't know what it is. That's why it is a research topic. We have to accept at some point that there are things we don't know. We might know in the future, but we don't know currently, okay? That's why it's a current research topic. I mean, there was a time when we didn't know that light can travel in a vacuum because of being an electromagnetic wave and has the speed of light in vacuum as a constant of nature, right? That was given to us in 1905. So things keep on evolving. We get a better and better understanding, hopefully, as time goes by. But there are things that we don't know, and that is okay. And this dark energy business is absolutamente one of them. Okay? I hope that you understand that that is the case. Dark energy, we don't know. Dark matter, we don't know. Okay? Lots of things we don't know. I mean, and this is just physics. There's so many things in other sciences too that we don't know. So it's nothing really new or that crazy. But in the sense of, when you understand the sort of enormity of it and how it affects things, it can feel a bit crazy, right? It's like, oh my God, 68% of the energy density contributed by dark energy, and we don't know what it is. Goodness gracious me. I understand the urgency that one might feel, okay? But at the same time, now I want you to consider some quantum mechanics. And we kind of know, and it is conceivable that space or empty space isn't really all that empty now, is it? We know that particles go in and out of existence all the time, especially pairs of them. Quantum effects like that is how we get black holes to have a temperature and eventually, evaporate and stuff like that. So it's not so crazy to wonder if there is something going on in empty space that kind of gives it this extra push or whatever and makes, space-time, makes the universe expand. So what could it be and what is it? One can certainly imagine something happening there, but at the same time, one would like to be sure. We wouldn't want to just think about it. We would want to sort of understand it better and measure it and all that stuff, right? So that's what's going on here. And he's going to talk about that there might be mysterious things going on in the vacuum causing this negative energy thing to happen. And that would be so fascinating to learn about, right? So that's what we're gonna do. So okay, let's go. This is bedtime reading for adults and kids. Okay, so go to bed and keep on listening to this by the bedside. So what is this stuff? We don't know. Maybe it's a quantum effect where the vacuum of space, instead of being empty, actually seeds with particles and their antimatter counterparts. We've talked about pairs of particles and their antiparticle partner, sometimes going in and out of existence, coming up, then annihilating. Those types of things we know about. They pop in and out of existence in pairs and don't last long enough to be measured. Their transient existence is captured in their moniker, virtual particles. So there's particles and then there's virtual particles. Virtual particles are the ones that are popping in and out of existence. We're not really measuring them or anything, but they're happening. They're there. They're doing stuff, but we can't really measure them. They're transient in nature. The remarkable legacy of quantum physics, the science of the small, demands that we give this idea serious attention. Each pair of virtual particles exerts a little bit of outward pressure as it ever so briefly elbows its way into space. So could it be, so there is something which is dark energy. Could the something be these virtual particles putting some outward pressure as they do this in and out of existence business? So we're trying to understand now what the something is, okay? What this mysterious dark energy is. What could be the source of it? What is the physical thing that's happening that leads to it? That is the topic, okay? Can we get 100 likes, please? So if the virtual particles were responsible, right? Unfortunately, when you estimate the amount of repulsive vacuum pressure that arises from the abbreviated lives of virtual particles, the result is more than 10 to the 120, so 10 to the 120 times larger than the experimentally determined value of the cosmological constant. Oh, way. This is a stupidly large factor, leading to the biggest mismatch between theory and observation in the history of science. So too much. So we're clueless. It's not abject cluelessness. Dark energy is not adrift with nary a theory to anchor it. Dark energy inhabits one of the safest harbors we can imagine. Einstein's equations of general relativity. It's the cosmological constant. It's lambda. Whatever dark energy turns out to be, we already know how to measure it and how to calculate its effects on the past, present, and future of the cosmos. Without a doubt, Einstein's greatest blunder was having declared that lambda was his greatest blunder. So it has this stable foundation, but we just don't know what it is. So the hunt is on. Now that we know dark energy is real, teams of astrophysicists have begun ambitious programs to measure distances and the growth of structure in the universe using ground-based and space-based telescopes. These observations will test the detailed influence of dark energy on the expansion history of the universe and will surely keep theorists busy. They desperately need to atone for how embarrassing their calculation of dark energy turned out to be. So lots of current efforts. We can talk about those as well, probably next time. I realize it is getting late here. Thank you. Hi, Ahmed. Hi, Wild and Fresh. Okay, we'll keep going. Do we need an alternative to general relativity? You know, the fact that we don't understand what dark energy is can be concerning to many, you know? It can mean that maybe we got general relativity wrong, you know? But the theory is so successful in so many ways. We've talked about so many predictions of general relativity coming true, even including but not limited to the gravitational waves that we measured some years ago, the bending of light that he had predicted, Einstein, and that was confirmed. So many of general relativity's predictions have come true that it would be, we don't have good reason to think that it's wrong, right? That's the issue. So you can't just say that GR is wrong and go away with it because just brush it off, because in so many ways it's not wrong. It's just that we don't understand dark energy. Thank you for the gift. Hi, Jerry. Thank you so much for the bronze medal. Thank you. Thank you, Jerry Mahone, for the gift. Thank you so much. Thank you, Wild and Fresh. Hello, Potato. Okay. Okay. So, is GR wrong? Is a question. Does the marriage of GR and quantum mechanics require an overhaul? Okay. Or is there some theory of dark energy that awaits discovery by a clever person yet to be born? Okay. We want to understand it. We don't yet. So we're wondering what it's going to take. A remarkable feature of lambda and the accelerating universe is that the repulsive force arises from within the vacuum, not from anything material. So we do think that it's coming from the vacuum and not from anything material. As the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. Because we do know about the most distant galaxies, they're receding even faster. So as the vacuum grows, the density of matter and familiar energy within the universe diminishes. So where there is familiar energy, we don't see this effect. We see it where there is less familiar energy. This is where it really takes off. So it's not the familiar energy that's causing it. It's the dark energy, which we don't know what it is, right? So once again, as the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. So if it were, thank you, Joe Dirt, for the super chat. Appreciate you. If it were some familiar energy that's causing this expansion, then the effect of it wouldn't grow as the vacuum grows, right? So as the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. With greater repulsive pressure comes more vacuum, and with more vacuum comes greater repulsive pressure. So it's kind of like building on itself. More vacuum, more of the pressure. More pressure, more of the vacuum. So this thing that has an anti-gravity effect grows with the vacuum, okay? Forcing an endless and exponential acceleration of the cosmic expansion. As a consequence, anything not gravitationally bound to the neighborhood of the Milky Way galaxy, like I was saying before with the local cluster, remember, will recede at ever increasing speed as part of the accelerating expansion of the fabric of space-time. So anything that is not bound to us by gravitation in our local neighborhood of galaxies will recede at ever increasing speed as part of the accelerating expansion of the fabric of space-time. Those are going to be gone bye-bye. And the farther away the galaxy is, it's going to be gone bye-bye even faster. So, thankfully we have neighbors, we have Andromeda, we have the local cluster. These things are held together by gravitation, and effect of gravitation is more here in this locality. But if you go farther out, what wins is dark energy. We don't know what it is, but it wins. There's more vacuum, more of the negative pressure, more of the dark energy, and those things farther away, going bye-bye, getting farther and farther away. Accelerating like, okay? So, distant galaxies that are now visible in the night sky will ultimately disappear beyond an unreachable horizon. This is where it's a little sad. So I know that this story, the way this chapter ends, is kind of sad. So I didn't want to finish it tonight because it's sad. But I'll finish it. Distant galaxies that are now visible. So you can see galaxies in the sky, right? Eventually, they will recede and we can't see them anymore because light can only travel so far. So we'll have less and less friends. Distant galaxies now visible in the night sky will ultimately disappear beyond an unreachable horizon, receding from us faster than the speed of light. A feat allowed not because they're moving through space at such speeds, but because the fabric of the universe itself carries them at such speeds. The fabric of the universe is getting stretched. Remember? The fabric of the universe is getting stretched. No law of physics prevents this. In 1 trillion or so years, anyone alive in our own galaxy may know nothing of other galaxies. Our observable universe will merely comprise a system of nearby, long-lived stars within the Milky Way. Because, those will be still gravitationally bound, but if you're not gravitationally bound and there's dark energy doing its work, then things are just going to get farther and farther apart. And beyond this starry night will lie an endless void, darkness in the face of the deep. Dark energy, a fundamental property of the cosmos, will in the end undermine the ability of future generations to comprehend the universe they've been dealt. Unless contemporary astrophysicists across the galaxy keep remarkable records and bury an awesome trillion-year time capsule, post-apocalyptic scientists will know nothing of galaxies. The principal form of organization for matter in our cosmos, and will thus be denied access to key pages from the cosmic drama that is our universe. Behold my recurring nightmare. Are we too? So this is where it gets really dark, pun intended. Are we too missing some basic pieces of the universe that once were? What part of the cosmic history book has been marked access denied? What remains absent from our theories and equations that ought to be there, leaving us groping for answers we may never find? So just like in the future, people might not know about galaxies because they have receded beyond to where we can't see anymore. And they might think that there are no galaxies because of that, as in beyond the Milky Way, that is. Similarly, well, we're here at some stage of this universe, and what parts of this universe are we not understanding because we can't see far enough away, and we don't have access to that information because we only have access to the information that can travel to us at the speed of light in a finite time, where things align where we can get that information. So it's a sad story. Sad story. Gravitation brings things closer. Gravitation is love. Dark energy is the opposite of it, if you will. Dark energy makes things far apart. So far that we may not even have access to these things in the future. Okay, that's that chapter from Neil deGrasse Tyson's Astrophysics for People in a Hurry. Quite depressing, my loves. And with that, we're done with this particular rendition of the topic. We've talked to, we can, I'm sure this topic will come back and we'll talk about it again and have other insights on it. But that's what I have for you tonight, okay? Let me know your thoughts, comments. Appreciate everybody being here. I will look at your comments. Thank you guys for the likes and comments. Good to see you guys. In Afrikaans, thank you very much. Hi, Rockstar. How are you doing? Thank you for coming back to the channel. Really appreciate you. Hi, Remix. Hello, something more. Hi, Mr. Vision. I would understand Afrikaan. Afrikaan is like, it has a lot of Dutch, am I right? It's Dutch and what else again? What are all the mixtures? Hi, Tony. Hi, Reappliance. I've seen a few episodes of Big Bang Theory. What's the TLDR? Hi, Cupid. Hi, Soph Vibes. Thank you. Love your hair and your shirt. Oh, thank you so much. Yeah, I wore this dark colored shirt with flowers for you guys tonight. It's a blouse shirt. Thank you. Can we get 100 likes, by the way? A milestone for me to get to. Proportional to inertia. So, gravitational force is proportional to mass. So this connection between the mass of something and its gravitational field is where the, I think what you're asking, somebody who asked it, spacecraft enthusiast, the small g, mg, equal to ma. That's what you're saying, right? Like the F equals ma in Newtonian mechanics. The F, when it's gravitation, would be the small m times small g, and the small g ends up being the acceleration. Is because when you think about gravitation as a force in Newtonian physics, which is not the case in GR, it really drives home the point that inertial mass is the same mass that is also the reason for gravitation. Okay, so that's a good question. Inertial mass being the gravitational mass leads to small g being equal to the small a in that F equals ma equation. Okay, so yeah, it's very important how massive something is for its gravitational effects. If you're listening to this while sleeping, good night and sleep tight. Hi, Farshid. Hi, Rockstar. Take a picture. Aww. We do take lots of pictures. German, Dutch, South African, Yiddish, all sounds the same. Yes, so somebody said, makes you think about what we already lost. Exactly. This really makes you think about what we already lost. Doesn't it? I told you guys that the universe is constantly evolving. So what we know now is just what we know now. It's evolving. Things will change going forward. Things have already changed. Hi, Mr. Vision. Your name is Andrew. Are you asking me or telling me? um, am I at 100 likes? Thank you. I'm only seeing 99, but okay. We talked about cosmology today. That was the topic. Dark energy. English comes from Yiddish. Thank you, Pumbafo. Hello. Thank you so much, everybody, for joining. As always, really appreciate it. I try to catch up with as many comments as I can. Sometimes they're a little distracting and I want to get through the topic, but I really appreciate all of you for joining and commenting and dominating the chat. Hopefully you made some friends and learned some new things. Love it. Please do like, share, and subscribe. Thank you so much. Good night and sleep tight. Thank you, Boo Boo. Hi, Unorthodox. Oh my goodness. We just finished our episode on dark energy part 2 in cosmology. You'll have to rewind, okay? How do I say my name? Oindre. Oindree. Thank you, guys.